Hello, everyone. Welcome to this WiCyS webinar with Sandia National Labs presenting on the topic of improving electric grid cybersecurity with cyber physical analysis. My name is Laura Villalobos, WiCyS Community Manager. With us today, we have Shamina from Sandia National Labs, who will be leading today's webinar. Before we start, I'd like to introduce a little bit about the WiCyS organization. We often go by our acronym WiCyS as in we and sisters, because that's exactly what we are, a global cyber sisterhood. We are a 501c3 with over 6.8 thousand members in 70 countries. WiCyS is a premier organization with global reach dedicated to bring together women in cyber. Our mission is to recruit, retain, and advance women in cybersecurity. All of our programs and initiatives are made possible with our supported strategic partners such as Sandia. We have our own professional affiliates, student chapters, volunteer committees, mentor-mentee program, job wars, member forum, and so much more. You can view our training programs and initiatives on our website at wicys.org to learn more about the different ways to get involved beneath the WiCyS community. All of our wonderful initiatives to our strategic partners, our tier 1 partners being AWS, Battelle, Bloomberg, Carnegie Mellon University Software Engineer Institute, Cisco, Fortnite, Google, Intel, Lockheed Martin, Meta, Microsoft, Optum, Sandia National Labs, and SentinelOne. Reminder to ask questions throughout the webinar. You can put them in the chat and the presenter will answer them at the end. We have the experts here with us today, and they look forward to hearing from you and the audience. If you haven't done so already, make sure to subscribe to the WiCyS newsletter at wicys.org to stay up to date for any upcoming WiCyS events and training. And with us today, we have Shamina Hussain from the Sandia National Lab.
Thank you so much. Well, yeah, again, my name is Shamina Hussain McKenzie, and I'm a cybersecurity researcher at Sandia National Labs. And today I'm going to be presenting on advancing the electric grid cybersecurity with cyber physical analysis. I'll stop sharing for now. All right. So to begin, I'll give a little background about me. So my educational background, I did my undergrad at Washington State University, and then I did my master's and PhD at University of Illinois at Urbana-Champaign, all of which I focus on electrical engineering. And specifically for my graduate school, I focused on power system analysis and control, especially when we have cyber attacks or other disturbances occur in the grid. And so for my work experience, I've been at Sandia for about 5.5 years now, and previously had internships at the Pacific Northwest National Lab, the Boeing Company, and the Energy Northwest Columbia Generating Station. And at Sandia, I am currently in the Cyber Resilience Department, and I am a principal member of the technical staff. And I'm originally from Richland, Washington, and I currently live in Albuquerque, New Mexico with my husband and my cat Momo, as pictured. And so my hobbies include adventures outdoors, which has been really great in New Mexico, cooking, and as well as traveling with friends and family. So before I begin, I'll give a little background on industrial control systems and cyber physical systems before we dive into cyber physical analysis for grid cybersecurity. So first of all, industrial control systems are control systems that are used for industrial process control. And this is really common in critical infrastructure systems as pictured here, which could include chemical plants, dams, government facilities, IT or information technology, and critical infrastructures such as energy or the power grid. And of course, water and wastewater systems. And so these industrial control systems are composed of different control devices, communication devices that enable decisions to be communicated to the end physical process. And so we are also focused on cyber physical systems, of which many industrial control systems are, especially as we're adding more communications and smart technologies to them. And so here's the definition of a cyber physical system from the National Science Foundation, or NSF. Cyber physical systems integrate sensing, computation, control, and networking into physical objects and infrastructure, connecting them to the internet and to each other. And so an example for the power grid is shown here, where we have a decision ladder a decision layer that is deciding different controls to communicate using the communication and coupling layer that is then sent to the power layer, to our actual physical and process components. And so an example could be through the sensing and the sensor data that is sent from the power layer to the decision layer, a decision could be made that we need to increase generation. And so from that is communicated through the communication coupling layer and the power layer, then that generation is increased. And so this is a very simple example of what a cyber physical system is and the type of interactions that can occur. And so in this talk, we'll be focusing specifically on the electric grid and its cyber-physical nature. And so the grid is becoming increasingly cyber-physical. And this is due to more modernization efforts and it rapidly evolving with smart grid technologies, having more wide area monitoring that's enabling that distributed sensing and advanced automation. And so we need to understand the impact from multi-hazard events. So we need to understand when we have, say, cyber attacks occurs, extreme weather events or equipment failure, not only how does it impact the physical system or the physical layer, but how does it impact the cyber system, the communication network, the control. And so as such, our main motivation is that we need to leverage cyber physical analysis for increased situational awareness, for improved response and increased resilience in the grid. And so today I'm going to be highlighting 4 different areas where we could include the cyber physical analysis, but this is not an exhaustive list. These are just some examples and will be highlighted in the projects that I talk about for the remainder of the talk. And so we'll be talking about cyber physical intrusion detection, cyber physical data fusion, cyber physical mitigations, and the characterization of cyber physical interdependencies. And so to touch on each of those, the first project I'll present is the PIDMS, or the Proactive Intrusion Detection and Mitigation System, that's going to focus on the intrusion detection. HARMONIE, which is going to be focusing on cyber physical response. Grid DNA, which is cyber physical data fusion. And Intergraph CPS, which is cyber physical interdependency characterization. And so this overview will definitely be a whirlwind of information for each of these projects. And I just hope I can impart the main message that cyber physical analysis is crucial for electric grid planning, operation, and response. But please ask me any questions, or if you need or are interested in additional resources, I'd be happy to share that as well for each of these projects. So I'll start with the Proactive Intrusion Detection and Mitigation System, or the PIDMS. And this was a DOE Solar Energy Technologies Office, or CETO project. And it was from FY19 to FY21. And we actually just recently got an R&D 100 award for it, as well as a silver special recognition as a market disruptor. And so the Sandia team is listed here. And we also partner with the Electric Power Research Institute, Opal RT, and DNK LLC. And so in this project, we focus specifically on distributed energy resources that are at the grid edge. And DERs have increasingly sophisticated functionalities that allow for autonomous and remote grid support services. And so this includes having advanced communication capabilities, more access interfaces, and third-party software. And of course, this is improving the grid operation and also the ability of the DERs to contribute back to the bulk power system. And so it's increasing the efficiency, it's increasing the connectivity. But one thing we must do as we add these new capabilities is understand how the attack landscape has been broadened, and specifically the communications and access interfaces associated with DERs, how can they be exploited? And so here in the middle box is listed some examples where there has been reported vulnerabilities in inverters that play a very large role in DERs and converting energy to be connected to the bulk power system. And then I have also listed the Ukrainian grid cyber attacks as well as Colonial Pipeline cyber attacks as examples of critical infrastructure cybersecurity events, and specifically in the Ukrainian grid cyber attacks, we saw that the power system was also impacted in its operation. So Overall, in developing the PIDMS specifically for DERs, we're focusing on defense of smart inverters, which play a prominent role in DER systems and need to be secured. And the compromise impact is growing as PV or photovoltaic penetration is rising. And this is also due to new standards like IEEE Standard 1547 that are mandating grid support functions. So we can have this automatic sensing and control. And so in this project, we are focusing on developing an intrusion detection and mitigation system specifically for PV systems, but of course can be brought into other DERs as well as transmission distribution system. So this project had three main objectives. So first was to develop the distributed bump in the wire sensors. And so we wanted to implement this on low cost single board computers. And this is so that resource constrained DER aggregators or private owners could also use the PIDMS. We wanted the PIDMS sensors to collect cyber and physical data, which I'll talk more about in future slides. And then enable peer-to-peer communication such that we had this distributed set of PIDMSs that could talk to one another and share alerts and share information, such that we had increased situational awareness and could also understand impact propagation of different events. For the PIDMS methodology, we tested various hybrid IDS approaches, including different machine learning techniques. And we evaluated the performance against diverse attack scenarios within an emulation environment. And within that, we also tested different mitigation strategies. And then finally, for the emulation environment, we use Minimega, which is a Sandia tool for virtual machine management. And we were able to model our communication network, which I'll show in the next slide. And every DER simulator to model virtual inverters, and OpalRT for dynamic models of our transmission and distribution systems. And at the same time, we could also hardware in the loop inverters and PIDMSs that were prototyped on those single board computers. So to talk a little bit more about the emulation environment, the communication network, as I mentioned in the last slide, was modeled in Minimega. As pictured, example environment is shown on the right here, where we could, in Minimega, model, the different communication network pieces such as routers and gateways, as well as control centers, and then also implement our virtual PIDMS prototypes, and also have virtual machines that were running every DER simulator that allowed us to simulate our DER or PV system, and specifically the virtual inverter. And within this, we could also implement some of the grid support functions. And this, the VMs for the EPRI-DR simulator were then connected to the distribution system, which was integrated with the transmission system within the OpalRT environment, which is a real-time digital simulator for power systems. And so all in all, this emulation environment allowed us to have a real-time environment where we could extract both cyber and physical data streams and understand how the PIDMS, both hardware in the loop and virtual, was performing when we tested it against different attack scenarios or other events. And so for the PIDMS sensor itself and its overall process, that's summarized in this top figure here, where the PIDMS queries inverters for physical data points. The network traffic is collected by Snort and Zeek, which are network IDS tools. And we use to be both our cyber data collection as well as our signature-based IDS, or intrusion detection system. And that data, that cyber physical data, is stored in an Elasticsearch database, and the machine learning algorithms process that, and resultant alarms and flags are shared through the MQTT protocol that are allowing us to have that peer-to-peer communication. And so, a simple example is shown in the bottom figure, where the PIDMS on a single board computer implementation is hardware in the, bump in the wire to that PV inverter. It can query the PV inverter directly for those physical data points. And then Zeek and Snort on the PIDMS itself is intercepting that traffic, the cyber traffic. And both that cyber physical data is processed from the Elasticsearch database using the machine learning algorithms. And as you can see, there's the MQTT broker and the publish subscribe framework to share that any alerts and other information with peer PIDMSs. So in this case, these two PIDMSs can talk to one another. And so this slide is just summarizing the PIDMS prototype design, which reiterates kind of some of the highlights that I presented in the last slide. And so the hardware PIDMS was implemented on a Raspberry Pi 4, and the virtual PIDMS was implemented in the x86 architecture for deployment within Emulation. And so for the single board computer deployment, we assess costs on board storage and computational burden for different machine learning approaches. But overall, that single board computer deployment was selected for this prototyping, and we mainly wanted to demonstrate that there's flexible options for deploying the PIDMS methodology. So it can be integrated in different devices as, say, a software container, but also could be integrated, say, in the inverter itself. So in the next slide, a little bit more about the PIDMS methodology itself. So it's a hybrid IDS approach, and this is both in that is signature-based and behavior-based, and it processes cyber-physical data. And so for the signature-based, again, we used Zeek and Snort. And then for processing the cyber-physical data and with the behavior-based technique, we use machine learning algorithms. And so we tested a variety: autoencoder, support vector machine, and adaptive resonance theory. And simultaneous online learning and detection via incremental learning was also enabled. So in that case, we could do our training and testing prior to installation in the field. But even after installation, it'll keep on learning and improving its detection accuracy. And just to highlight, we ended up using the adaptive resonance theory artificial neural network due to its ability to alert on the cyber physical data, but as well as its performance on the single board computer, as I mentioned a couple slides ago. And so if you see in the right figure here, the overall process for the PIDMS is highlighted, where we collect cyber and physical data. We perform the hybrid IDS analysis, we detect an alarm, and when suitable, we can deploy a proactive response and continue that process. And to highlight some of the PIDMS cyber physical mitigations, so this is not an exhaustive list, but just to give an example why it's powerful to have both cyber and physical mitigations available for grid IDSs. And so for cyber, we had different firewall rules like blocking or dropping malicious packets, blocking attacker IP addresses. There were some custom rules that we could also leverage from Zeek and Snort. For physical mitigations, we focus on restoring control operations, resetting default or backup settings. We also explored using machine learning, the laterally primed adaptive resonance theory artificial neural network to resume control. So it could actually predict for certain grid support functions what the next control should be, given that control was interrupted, say, by a denial of service. And then finally, an example of a denial of service interrupting communications and increasing round trip times is shown in this table here, where we have almost no response during the DOS without the PIDMS and with the included and no mitigation. And during the denial of service, when we did deploy mitigations, we were able to restore that round trip time to close to what it was before the denial of service. So 0.531 milliseconds compared to 0.558 milliseconds. And so before I move on to the next project here, I'll also look at the chat. I think I saw a question. There's a question: are there any government policies that are driving requirements into intrusion detection and mitigation? That's a great question. So first of all, I think there has been some work in this case, because the PIDMS was focused on DERs and photovoltaic systems, or PV, looking into DER cybersecurity requirements. And so there are standards that I believe different, like SunSpec Alliance, are looking into developing. And I think they've made a lot of progress on that. And then otherwise, for the grid support functions themselves and those automated controls that might also address some of these cybersecurity concerns, standards like the IEEE 1547 are working on that as well. And yeah, thanks for your question. And let me know if anyone has more questions. I'll be happy to address, and I can also address them at the end of the presentation. Yeah, so next I'll talk about the HARMONIE project, which is a harmonized automatic relay mitigation of nefarious intentional events, special protection scheme, so HARMONIE SPS. And so to reiterate, the PIDMS focused on how do we use cyber-physical analysis for improving intrusion detection for PV systems, or in general, the DER systems. For HARMONIE SPS, we focus on transmission systems and looking at special protection schemes that are already in use. They're also known as remedial action schemes, or RASs. And we wanted to look into how can we make that analysis cyber-physical, and how can we make it adaptive such that it can respond to unpredictable events such as cyber attacks. And so this is a Sandia Lab directed research and development project, or LDRD. The Sandia team is listed, and we also partnered with Texas A&M University, and this was FY21 through FY22. So to begin, as I mentioned, SPSS or RASs play a large role in the power grid already, and they are leveraged by utilities to maintain stability, acceptable voltages, and loading limits during disturbances in the electric grid. And so they operate in a playbook manner where they detect predefined abnormal conditions, which these triggering conditions are defined in extensive planning studies prior to operation and deployed. And once those are detected, they deploy predefined corrective actions. And so this works really well for attacks or events that we expect to happen. And then one more thing to note is SPSS or RASs can take actions beyond isolation of a fault and include changes to demand generation and system configuration. So much larger control or corrective actions than, say, just a regular protection. And traditional SPSs are unable to defend against unpredictable disturbances. And so when we have events such as extreme weather or cyber attacks occur, we cannot predict the trajectories they will take in advance. And so it's hard to define what those triggering conditions will be. And so a next generation SPS is needed that can adapt to unpredictable events and be able to classify those system conditions in real time, and such that we can effectively respond to limit or eliminate the disruption quickly. We need a SPS that is cyber physical in analyzing collected data. And again, for the high overall message that the grid is more cyber physical, and with this increase in cyber attacks and this dependence between the cyber and physical systems, it's important that we monitor both domains. And then an SPS that extends the use of protective relays from fault isolation to also adaptively learning system conditions. And that way we can help prevent cyber attack propagation and take proactive actions to prevent compromise within the relay set itself. And so this slide gives a summary of the HARMONIE SPS approach. And so if you see the white flow chart on the left, cyber physical relay and other data is collected. That data is then classified to determine some conditions. And that classification determines prioritization of selectivity, security, and speed, or speed. And prioritization determines then what response we take. And so, for example, in the yellow box, the data collection from the digital relay could include physical data such as current, voltage, frequency, and fault data logs. But additionally, we'll also want to look at the cyber data, so communication traffic, setting files, device configuration. We could also use data collected from different PMUs or phaser measurement units, similar physical data, and then also add any out-of-band data such as from intrusion detection systems when we have alerts or warnings, and could also detect relay compromise. And so overall, this cyber physical data is then processed using machine learning algorithms, which I'll touch on in the next slide, that to classify if we're in normal operation, cyber disturbance, physical disturbance, or cyber physical disturbance. And this really helps us understand our prioritization of security, selectivity, and or speed. And also when we need cyber responses or like corrective actions, and when we need physical corrective actions, or when we need both. So I won't go into too much detail here in interest of time, but overall for the HARMONIE SPS classification framework, the main goal was to develop a joint model of the cyber physical information using an integrated data framework. And this would allow us to have downstream prediction of anomalous events. And so again, we have the 4 different classes. But what we needed for our machine learning approach is one that is able to integrate this disparate data, the cyber and physical data, but also be able to deal with the temporal changes. And so for that, we looked at using the graph convolutional neural network approach, as well as a transformer-based neural network approach to help address those challenges. And if you're interested, we have some papers that describe this further, as well as the whole project report. And so for the corrective actions, again, here we're listing different actions that we explored for this HARMONIE SPS. Not an exhaustive list, but to give an example of when we need cyber and physical mitigations. And so for the cyber mitigations, we had different firewall rules like blocking attacker IPs, dropping malicious traffic, but we also developed a traffic routing optimization algorithm, especially when we have injection attacks, and that's one we developed with Texas A&M University. For physical mitigations, we can leverage some of the classic SPS or RAS corrective actions such as line switching, load shedding, changes to generator set point, but also in conjunction with Timu, we developed the auto-RAS approach that uses support vector machines to automatically assign corrective actions to triggering conditions based on clustered violations. And so this really helps improve that extensive process in the planning stage of assigning what corrective action would help this predefined triggering condition. And so we were also able to test that within our emulation environment. And then finally, the cyber physical mitigations could be a combination of the above listed, but we also developed a relay voting scheme that incorporates cybersecurity information, which I'll talk a little bit more about in the next slide. So the consensus-based automatic relay voting, or CARV scheme, is a next generation relay voting scheme that extends traditional 2 out of 3 voting that relays often use. And in this case, leverages consensus algorithms to incorporate inter-relay relationships and out-of-band data. And so we're also able to do distributed calculation of system values, such as a power system state, for example. And this helps prevent common failures from centralized failure points. And so all in all, no decision is taken without ensuring majority relays agree on the protective action. And this process is shown in this flow chart here. But the overall idea is that the CARV enables relays to verify and check each other's actions and alert when relays within the voting scheme fail to operate correctly, whether it's from equipment failure or from a cyber attack or compromise. And so for the HARMONIE SPS project, we developed a cyber physical emulation environment using RTDS, a real-time digital simulator, very similar to the Opal RT, and Scepter, which is a Sandia ICS emulation tool that allows us to model the SCADA system of different ICSs and connect it to an end process simulation model, which in our case was RTDS for the power system. And we modeled different disturbances, collected real-time data, and tested HARMONIE SPS classification of those different disturbances. And also when mitigations were deployed, did they actually help improve the system conditions? And so this emulation environment allowed us to have both virtual and hardware-in-the-loop devices. And we could also implement Modbus, DNP3, and C37.118 communication protocols. And so overall, we tested in the emulation environment 2 different use cases. One was the WCC 9-bus system shown on the bottom left, and the other was the larger IEEE 39-bus case shown on the right. And for each, we developed a representative communication network as well, and implement it within our environment to have a cyber-physical real-time environment. And so in the WCC 9-bus system, we modeled the denial of service attack, a generator and line outage, as well as a denial of service plus those outages to highlight cyber disturbance, physical disturbance, and a cyber physical disturbance. And we were able to classify each of those correctly and also deploy the mitigations that did improve the system conditions. For the false data injection attack, we implement this in the IEEE 39-bus case. And we only tested the mitigation due to time constraints, but we wanted to test this case for testing the traffic routing optimization algorithm when we detected a false data injection. And I'll check the questions again before I proceed forward. Let's see. So yes, are you open to accepting help from non-science background women? Yes, of course. And one thing I should have highlighted as I presented the title slides of each of these projects is this is a very interdisciplinary project. We have a lot of computer scientists, of course, who are experts in cybersecurity and designing these emulation environments. But we also have the power engineers, as well as folks who are working on, say, the protection algorithms, in this case of HARMONIE. But one thing we're really interested in diving into as we go deeper into the cyber physical analysis is how do we do human in the loop modeling? How do we ensure, especially in industrial control systems like ICS, there's a lot of operator interaction as well as control engineers. And so how do we model those? How do we understand how our solutions can be helpful? So to be sure, yes, we are very interested in having help from a broad array of expertise. And so another question was in US electric grid security. Oh, is US electric grid security at par with other countries or better than other countries? Can you share the name of countries whose electric grid plans impress you? I guess I don't think I know enough about other countries to comment on that. But I do know that here in the US, we are making it a priority to address this since, as we've seen with a lot of recent events, cybersecurity attacks are on the rise, and we do need to secure critical infrastructure. So I am proud that we have a big effort moving forward on trying to secure the grid and interconnected critical infrastructure. And then finally, how are wireless technologies such as Zigbee, Wi-Fi, etc., used in grid or sensor environments? How do these wireless technologies change the approach to cyber physical security? And so I know a lot of these Zigbee, Wi-Fi protocols are often used in DER systems or building automation systems. And so they are definitely here in the grid environment, especially in this integrated grid environment. And I think it wouldn't change our approach to cyber physical security. What we would still want to highlight the need of cyber data as well as physical data, but we'd have to build new tools, in our case, for what we've developed for PIDMS and HARMONIE so far, to be able to process, say, that Wi-Fi or Zigbee traffic. So it's something we haven't done yet, but something we're interested in. So thanks again for your question. All right. So I'll move on to the next project now. And again, I'll highlight what each one was since I know I'm giving an overflow of information. So PIDMS, again, was that cyber physical intrusion detection, especially designed for PV systems or DER systems. HARMONIE SPS looked at developing an adaptive cyber physical special protection scheme designed for transmission systems. And for Grid DNA, what we want, our focus is to develop a multi-level cyber physical sensor data fusion for situational awareness into decentralized electric grid, where we're focusing on multiple levels of the grid. So not only transmission or DER, but transmission, distribution, DER, and how they interact with one another. And so this is also a Sandia LDRD project. And the Sandia team is listed below, and we partnered again with Texas A&M University, as well as SNC, a Sierra Nevada corporation, Tenable, and the Public Service Company of New Mexico, who is our local utility. And so this project actually just started a few months ago in October, and will be going on for 3 years. And so to begin, for Grid DNA, we're proposing a novel fusion of both cyber and physical data from different levels of the grid for comprehensive cyber physical situational awareness, or CPSA, to inform planning, operation, and mitigations. So we're not only focusing on the response side of things, but how do we also help with the CPSA planning and operation? And so the Grid DNA sensor will not only collect cyber physical data concurrently, but also perform onboard correlation analysis in real time. And this onboard data fusion analysis in the Grid DNA sensors provides local CPSA. And so that local CPSA information can then be aggregated such that we have global CPSA, and with the ability to zoom into different areas of the grid, as the below picture highlights. And so this would help us to have initial indicators of a widespread event and ability to potentially mitigate before propagation. So the 4 main goals of this project is to develop sensors that collect cyber-physical data at different grid levels, both hardware and virtual prototypes, to develop the implementation architecture of sensors at each level that defines sensor placement for full cyber-physical observability, and secure data exchange between sensors. And again, this is because we're not only considering one type of system, but we want interconnected systems that potentially may have different ownership as well. And then sensor data fusion techniques that focus on analyzing multi-level cyber-physical data and also take into account the decentralized nature of the grid. And then finally, performing both cyber-physical emulation and field testing of grid DNA, which I'll discuss more in later slides. So the grid DNA sensors are actually going to be leveraging the existing PIDMS sensor design, as shown in the right. And specifically, its ability to collect cyber-physical PV inverter data. As you recall, it could query the inverter directly for those physical data points and use Zeek and Snort to collect that cyber traffic. And so we'll be extending this design to also adapt to transmission distribution system levels and different types of devices. For example, if we had the grid DNA sensor co-located with a PMU. And so we'll be extending it to do multi-level grid data collection. And also, not only we can leverage some of the RAN, LibPAR-AN machine learning algorithms that was used for detection, we also want to put in our data fusion analysis approaches as well. For which we are looking into different machine learning approaches, including the existing ones we already looked at, but also adding to it with numerical analysis techniques like principal component analysis and other graph theoretic decomposition techniques. And so another aspect that we're exploring for the sensors is for achieving remote and secure connectivity of sensors. And we want to understand how would we deploy grid DNA on existing grid security devices. Would this be a software container? How can we integrate it with, say, a device such as a binary armor that SNC or Sierra Nevada Corporation developed? And so we're partnering with them to explore what that would look like and also to inform just a general design of how grid DNA can be used. And so for the implementation architecture, we'll be defining grid DNA sensor placement for achieving that multi-level CPSA. And we'll be leveraging some control theoretic concepts such as system observability to understand where do we need to place a grid DNA sensor such that I have sufficient cyber data and physical data to say I have a complete CPSA or cyber physical situational awareness. And then for the secure data exchange between the grid DNA sensors, we're exploring different techniques such as distributed ledger technologies, single board computer options, as well as encryption options, to understand how we can provide trusted CPSA between utilities, aggregators, and DER owners. And so an example of that is shown in the below figure where we have a utility and say a privately owned DER system, and the grid DNA sensors will want to communicate to one another using peer-to-peer communication. How do we enable that with a secure implementation? And so that's one reason we have partnered with Tenable, who specialize in cyber exposure and cyber situational awareness, due to their experience with multi-site architectures. And one thing to note, we're finishing up a conference paper right now that should be presented in March that is touching on some of that secure data exchange framework that we are starting to develop. And so for the cyber physical data fusion, we're focusing on diverse disparate data and inference tracking approaches. And so again, we can leverage some of the classification approach from HARMONIE, as well as the PIDMS machine learning algorithms, as well as some of our partner TAMU's cyber physical modeling research. And so we're looking at techniques such as ordered weight averaging and belief propagation, but emphasizing how do we fuse disparate diverse data types and have accurate inference of cyber physical interactions. And so in the image here below, highlighting we want local and global CPSA, and so that we can zoom into different parts of the grid and understand propagation of disturbance impacts. And then finally, for the emulation and field testing, we'll be leveraging some of the emulation environments we already developed, as I mentioned, with the PIDMS, as well as the HARMONIE projects. And our overall goal is to be able to test within an integrated environment, grid environment with high penetrations of DERs, and look at both flexible options of hardware and virtual sensor implementations. And so, as I mentioned, we'll be performing some field testing with our partner, our local utility public service company of New Mexico. And an example test setup is shown on the right, where we may be able to use their Aztec data center as well as their Prosperity PV site to implement the grid DNA sensors. And we essentially want to assess the performance and suitability in a real utility center setting, and be able to also explore any needs for field installation and further validation of the design phase. And so any results from this will help further development of grid DNA to increase its adaptability and its scalability. And again, before I proceed, I don't think any new questions. But finally, the last project I'll highlight is the InnoGraph CPS approach, which is a graph theoretic approach to characterize cross-domain cyber-physical interdependencies and uncertainties in electric grid systems for improved decision-making in operation and response. And so this is another Sandia LDRD project, and it just started a few months ago as well, and will be going on for 3 years, FY23 through FY25. The Sandia team is listed, and we have again partnered with Texas A&M University, Southwest Research Institute, and Emera Technologies. And so, again, to connect with all the other projects, as I mentioned, in Grid DNA, we're interested in understanding some of the cyber physical system interactions and understanding impact propagation. Grid DNA is only focusing on that cyber physical situational awareness, the data fusion. In InnoGraph CPS, we want to dive in even further and understand, is there a way we can model the interactions between the cyber and physical systems in a mathematically rigorous way, such that we can understand if there even can be, say, an interdependence for certain scenarios. So to dig into that a little deeper, again, cyber physical observability, as I mentioned, is an important concept, how to understand we have enough data for, say, our intrusion detection or situational awareness applications. And so we did start looking into defining what does it even mean to be cyber physically observable, using a graph theoretic approach where we'll be able to combine cyber and physical graphs for the power system and communication network. And we could understand, okay, what nodes are connected to one another, what data would we need from what nodes. But one thing we didn't look at is now the data, the cyber and physical data streams, how do they interact with one another? Do they have any dynamic interaction? And so our main goal in understanding those CPS interdependencies is, one, how do we blend those cyber and physical data sources and use that to assess critical infrastructure interdependencies, and 3, characterize CPS features in systems. And so, as I mentioned in previous work, we looked at defining cyber physical observability, or CPO, but we didn't investigate the interdependencies between those nodes and the formal definition. And in existing CPS analysis and interdependency research, the focuses have been on characterizing that general nodal architecture of CPSs, and or looking at more the direct relationship between a controller and power system impact. And so there has been some quantification of dependability and interdependency models for large-scale cyber physical systems, and using causation and correlation techniques. However, we want to dig a little deeper than that and understand how the cyber communication network and the physical components in the power system interact with one another, or have a framework to analyze that to say when they do and when they don't. And so this prior research is really helpful and we'll be leveraging, especially for the graph theoretic analyses. And we want to add to that to gain some deeper insights. And so finally, to address the complexity of future CPSs, one of the papers that I mentioned here by Torngren and Grogan identified 3 main research thrusts. So 1, increase awareness of complexity and impact to CPSs, as well as establishing best practices for design and operation. Research into new knowledge, methods, and tools for CPS engineering. And then 3, research into organizational approaches and processes to adopt newly developed methodologies, permit effective collaboration between stakeholders, and also have more insight into these human-in-the-loop systems. So in this intergraph CPS approach, we are focusing on that first and second requirement, providing those new methods and tools to aid CPS engineering and rigorous insight into the complexity of CPSs. And so I'll just go quickly through this slide, but an example is shown on the bottom of a cyber-physical microgrid, where we might have different devices within our cyber domain and different generator load line components in the physical domain. And so we have ways to understand dynamic nodal relationships within, say, the physical domain or within the cyber domain, but how do we connect the two and understand the cross-domain relationships? And how does a local decision in one domain impact the global system, the global cyber physical system? And so we want to be able to answer questions such as, do I need more redundant pathways between certain nodes? Does a certain node have, a cyber node have an unintended impact on a physical node or vice versa? And so for intergraph CPS, we hypothesize that a graph theoretic modeling approach leveraging numerical analysis and decomposition techniques can be developed to assess cyber-physical interdependencies and dynamics. So this project has two thrusts. One is to develop the intergraph CPS approach itself to characterize the CPS rigorously, and which includes the cyber-physical interdependencies. And then two, the intergraph CPS approach will be developed with a unique set of UQ methods or uncertainty quantification methods suitable for assessing critical CPS features within the grid and informing grid operation and response decisions. And so overall, this approach can help identify weak points where the system needs hardening, develop improved mitigation strategies to increase grid resilience, and overall help all planning, operation, and response. And so a little more detail about each of these thrusts. In intergraph CPS, we're building on that prior CPO research and focusing on cyber-physical interdependency analysis and characterization of the CPS features, and essentially to understand what data features are transferred as system boundaries, how disturbances cascade between systems, and how can planning or mitigation measures leverage that type of information. And so we actually also had a conference paper that will again be presented in March that started looking at different characterization approaches, including we looked at ecological network analysis, we looked at coupling functions, K-shell or K-core decomposition, and principal component analysis. And so that was a start to our characterization approach. And then for the novel UQ methodology, we're going to develop one that can help us observe how limited observability scenarios affect the confidence of understanding the system states, and also can employ some of the sensitivity analyses to validate the intergraph CPS results using the emulation ground truth data, which I'll talk about more in the next slide. But all in all, our main goal with the UQ approach is to enable evaluation of how well decision makers can use the intergraph CPS interdependency results to inform decisions such as topology changes, identification of critical components, or mitigation design. And so finally, a little more about the emulation testing itself. Again, we'll be leveraging some of our existing environments for that initial testing. So for example, that paper I just mentioned where we looked into, say, principal component analysis and ecological network analysis, we use one of the HARMONIE WCC 9-bus environments and the data sets we already had from that. But we're also planning on implementing a new environment that will be using the Emera Kirtland Air Force Base microgrid model as pictured below. And this is a microgrid that is actually on the Sandia campus. And we'll be modeling that within our emulation using OpalRT and Scepter. And so we'll be able to model the communication network as shown on the right. And so this will allow us to model different events and different disturbances and assess the intergraph CPS ability to model those CPS interdependencies and study how impact propagates between the cyber and physical domain. And so those are the 4 projects I wanted to highlight. Again, I know that was a lot of information, but the main points I wanted to impart were that cyber-physical analysis is crucial for grid and interconnected critical infrastructure. And so it's really important that we, for cybersecurity applications, leverage existing understanding of physical end processes, since we have a wealth of knowledge, say, for example, in power system dynamics and control. How do we incorporate that in our cybersecurity detection tools or our response tools? It's also important to study interconnected systems and how cyber-physical impacts propagate. And then finally, by starting to generalize cyber-physical analyses, such as what we're doing in the Intergraph CPS project, we need to formulate how we can use those to be applicable to a variety of different systems, especially in the critical infrastructure domain, or when we start wanting to look at interconnected critical infrastructure systems. So for example, if we had our power generation and our natural gas system. Secondly, we want to incorporate deployment details from design phase to develop cohesive cyber-physical analysis framework. So it's really important as we're doing this early R&D that we do field and emulation testing to understand any constraints or needs that we need to think about early on. And also explore virtual and hardware implementation options such that we have flexibility in porting the solutions into different domains as well as different use cases. And that's all I had. Thank you all so much for listening and for your great questions so far. I'm happy to take more questions. And please reach out if you want any other resources or have anything else you'd like to talk about.